Hey nerds, we are getting back to graphing rational functions today. And actually today will be the first time that we actually start graphing what would be considered rational functions, whereas yesterday we were doing a special classification of them called reciprocal functions. Yesterday what we were working on were things that were constants on the top and a linear on the bottom. And those are called reciprocal functions when they're written like that. Okay. So this is standard form for a reciprocal function. This was not standard form for a reciprocal function. So the way it's written like this could be considered what we just call a rational function, meaning something generic that has x's in the denominator. But when it's linear on the bottom and constant on top, it can be classified as a reciprocal. But what happens when they're not just linear? What happens when we start having things with exponents in the denominator and the numerator? I mean, we can go completely bonkers. You know, so anything that has x's in the bottom can be considered a rational function. Once you determine domain, and domain for these things is always found the same, it's what makes the bottom equal 0 because those are not allowed. You know, that's not going to change. Once you've determined your domain, the next most important thing to decide on is the behavior of this graph. And you might have remembered in yesterday's lesson, I was drawing the behavior. But that's because for reciprocal functions, it's very simple behavior. You're guaranteed to have just two pieces and more. And for just reciprocal that's linear in the bottom, you're guaranteed that they're always going to be in the diagonal zones from one another that the asymptotes created. But when they're not just linear, when we've got more going on, we can have extra asymptotes, which means we can have more than just two pieces. So we really need to have an idea of how they're going to behave. And the best thing that we can do with that is talk about their end behavior. What's going on as x goes to negative infinity and x goes to positive infinity? What's going on? And there are some generalized rules here. And as far as memorization is concerned, yes, you would need to memorize these things. I prefer that you know why they have to be true. But if you're not the kind of person that cares why something must be true, you're going to have to memorize these three rules. Okay? All three rules deal with the degree of the top and bottom of the fraction, the degree of the numerator and the degree of the denominator. We're going to say that n is the degree of the numerator. That would mean the largest exponent if the numerator is written in standard form, the largest exponent of the numerator. And m would be the largest numerator of the denominator as long as it is written in standard form. So what we talked about in chapter 4 with behaviors of polynomials. Now we're talking about what if I've got a polynomial in the numerator? What if I got a polynomial in the denominator? We're going to look at degree of top over degree of bottom. So oh, and I forgot to say, we won't say horizontal asymptote unless it is horizontal, because not all end behaviors are horizontal. So the more generalized terminology will be the end behavior asymptote, because it doesn't have to be a horizontal line. It could really be any type of polynomial graph. Our end behavior asymptote could be any type of polynomial graph, which is why we do this material immediately following the polynomials chapter. If the degree of the numerator is less than the degree of the denominator, like this. The degree of this numerator is 0 because it has no x's. The degree of the denominator is 1. If the degree of the numerator is less than the degree of the denominator, then your graph does have a horizontal asymptote. Its end behavior asymptote is horizontal, and it's automatically going to be the line y equals 0. Automatically. You can memorize that, but I think it's important that you understand why that must be a truth. Imagine x is a ridiculously, catastrophically large number. We're talking about 100 bajillion, trillion, quadrillion, right? Like numbers that don't even exist. It's friggin' big. If it is stupidly large, does it make sense if I tell you that the +3 really doesn't change much? Like if you're the richest man on the planet, do you care if $3 fall out of your pocket? Or woman, richest woman on the planet? You don't, do you? Because as long as x is sufficiently large enough, the plus 3 really doesn't mean anything, does it? So imagine x is so big that you could do this. Now imagine there's only $2 on the entire planet. $2 on the entire planet. And all 7.5 billion of us had to share those $2. How much of it would you basically have? If there was only $2 on the planet and everybody on the planet had to share them, how much of it do you have? None, basically, right? Essentially zero. So this is why y equals 0 is automatically with a horizontal asymptote. Because what we're saying is when x is stupid big, these values are going to get closer and closer and closer to, well, 0. Because the bigger this denominator gets, the more people had to share those $2, the less and less and less you get, to the point where you basically have 0. It'll never equal 0, but man, it'll try to get close, won't it? So yeah, you could memorize it or you could understand it. When the degree of the numerator is less than the degree of the denominator, it automatically has a horizontal asymptote at y equals 0. The next rule, when the degrees are equal to each other, you will have a horizontal asymptote. Your in-behavior asymptote is horizontal. And it's going to be the fraction leading coefficient divided by leading coefficient. For example, here, the top and bottom were both degree 1, linear over linear. As x gets remarkably big, the -2 and the -7 start to mean very, very little, don't they? If you were the richest person on the planet, would you care if you lost $2 or $7? Of course not. So if x is large enough, the -2 and the -7 don't mean anything. And if you reduce this fraction, what do you get? Reduce this fraction, what do you get? 3. That's why it's leading coefficient divided by leading coefficient when the degrees are equal. So again, you could memorize it or you could understand why it's true. The one that is new for us today, though, is what if the degree of the numerator is larger than the degree of the denominator? We will only, in this course, allow the numerator to be 1 larger than the denominator. And if it is 1 larger than the denominator, then your in-behavior asymptote is actually a linear equation, y equals mx plus b. We say this is called a slant asymptote, also known as an oblique asymptote. Now, if it was more than 1 larger, then it would be polynomial in-behavior asymptote. Either way, you're going to have to find them using long division, but in our course, we will not go above the linear asymptote, known as a slant or oblique asymptote. In pre-calculus, you do go higher. You can have quadratic asymptotes or cubic asymptotes. You could really go as crazy high of a degree as you want to, but we won't in this course. We'll stick to linear in-behavior asymptotes. So either horizontal or y equals mx plus b. We already know what behavior is going on with vertical asymptotes. We know that that's where you're trying to divide by 0, as long as it wasn't simplified. But if you have degree 2 on the bottom of a fraction, or degree 3 or degree 4, you can have more than 1 vertical asymptote. Essentially, every time you try to divide by 0 without canceling it, you have a vertical asymptote. So that's not new. Just seeing more than 1 is new. X-intercepts, that's the same for all graphs. It's where your graph crosses the x-axis. And if you're crossing the x-axis, well, y is 0. But the only way a fraction can have a value of 0, see, y equals, the only way the fraction can have a value of 0 is if the top could equal 0. That's just common knowledge, logic. It has nothing to do with what we're currently learning. Y-intercepts, anytime you're on the y-axis, again, common knowledge. If you're on the y-axis, then x is 0. So for any kind of function you ever deal with, just plug in x equals 0 if you want to know where the y-intercept is. It's that easy. There's only one other thing that isn't in this box that we must discuss, and that is what happens when an x crosses off of the bottom. Like when we had to do multiplication and division of rational expressions, or when we had to do addition and subtraction of rational expressions. Anytime you cancel an x off the bottom, you now have an x that you know you're not allowed to use, but the final equation doesn't show it off. We call that a deleted point, a hole in the graph. It's also known as a removable discontinuity. So that's all the vocabulary for that. So will there occasionally be times when there's x's you're not allowed to use, but you can't see it because they got crossed off? Yes. We will deal with that in the notes. It won't happen today. You'll see it in the next day when we finish these notes. Hopefully Monday, because we're not going to finish them today. So let's just get into it. Here we have a rational function. The first thing I'm going to do is write it as a stacked fraction. I typed it this way to save space, but I'm going to write it as a stacked fraction, and I'll say y equals instead of f of x equals. X squared plus x minus 6. There. Before we do anything to it, let's decide on our end behavior. And the reason why we do that first is because once you factor it, you won't be able to see the degree of the top and the bottom as easily. So we're going to decide on that first because we can see the degree of the top is 1. And we can see the degree of the bottom, the denominator, is 2. What we have here is the degree of the top being less than the degree of the bottom. So again, you could either memorize what that means, or you could logic your way to what that means. Allow x to get remarkably, remarkably big. If x is large enough, the minus 6 and the plus 1 mean absolutely nothing. Can we agree to that? Okay. Can you see that you could factor an x off the bottom here? And it would cancel the x on the top? So that means you have 1 over, and on the bottom you still have an x, don't you? It'll be here-ish. So allow x to get remarkably, remarkably, remarkably big, and essentially you have a 1 over something that still has x's. So a 1 over remarkably big number. And the larger that denominator gets, the more this fraction is going to start to equal what? 0. So because the degree of the top is less than the degree of the bottom, our end behavior asymptote is horizontal at y equals 0. Before we, actually it doesn't really matter if you factor now or if you factor later. Let's go ahead and factor so we can figure out our vertical asymptotes. And maybe deleted points if they exist for this one. The numerator is what it is, x plus 1. The denominator, though, two numbers that multiply to negative 6 and add to 1 are 3 and negative 2. Nothing cancels. Unlike yesterday, I now have 2 numbers that would make the denominator equal 0, and you cannot divide by 0. And those 2 numbers that make the denominator equal 0 will be vertical asymptotes. So x equals negative 3 and x equals positive 2. So it's new that you have more than one vertical asymptote, but whatever. We talked about it yesterday. If it makes the bottom equal 0, vertical asymptote. You're not allowed to divide by 0. End behavior asymptote instead of horizontal asymptote. This end behavior asymptote is horizontal, but end behavior asymptotes could be anything. They could be horizontal, they could be y equals mx plus b, they could be ax squared plus bx plus c. Yes, I'm talking to Allie. She's completely ignoring me while she's on her phone and I'm teaching. But they could be anything. That's probably why you didn't catch that the first time I said it. And 2. There we go. So my my asymptotes have divided this thing up into 6 sections. We will be in at least 3 of them, at most 4 of them. Okay? You could just start grabbing random x's and plugging them in and hope for the shape to show itself. But I do think it's important that you always be able to track down both the x and y intercepts. So let's do that first. Let's find ourselves a y-intercept, because that one's easiest. Why are there 2 vertical asymptotes? Because there are 2 numbers that make me divide by 0. There could be 3, 4, 5, 6, 7. There could be as many as I want there to be. If it makes the bottom equal 0 and it doesn't cancel out, it's a vertical asymptote. Y-intercept requires you to be on the y-axis, which means you have no x value. So use x equals 0. Look up to that fraction. If x is 0, what's left on top? 1, and what's left on bottom? -6. You get 0 plus 1, and 0 plus 0 minus 6, you get -1/6. This graph crosses the y-axis at -1/6. That feels like -1/6 right there. Now, let's see if we have an x-intercept. You might be thinking, but Mr. M, the x-axis is a horizontal asymptote. Doesn't that mean the graph does not touch the x-axis? No, that's not what that means at all. Remember what I told you, an asymptote by definition is just a line or a structure that you will get close to when x is really, really, really big. It does not describe any behavior when x is small, like 0. So let's see if we have an x-intercept. If you're on the x-axis, you know y equals 0. But y is a fraction. So what is the only way I could get a 0 out of this fraction? What's the only way a fraction can equal 0? If the top is 0. Well, what makes the top equal 0? X equals -1. This graph hits the x-axis at -1. Told you a definition of an asymptote is something that your graph is going to get infinitely close to. And I can see that as I go to the left of this point, I have to go up to get to this dot. And I have to get infinitely close to this. So that automatically forces my graph to look like this. So I know that much at least. But to figure out more of this graph, I don't have an option. I have to literally plug and chug. I have to take some x values and I have to plug them in. What we need is an x value to the left of this red line, an x value between here and this red line, and an x value to the right of this red line. And let me tell you why we need those 3 things. When you're on the outside of the structures, so don't look in between. When you're on the outside, your graph will either be above or below the horizontal asymptote. It's just how it's going to be. It's either going to be above it or below it. It won't be both. Okay? So I need a number out here to figure out if I'm up here or down here. I need a number over here to figure out if I'm up here or down here. The reason why I need a number between here and here is because I don't know if this graph goes back up or if it goes down. So I just have to figure that out. I know I'm getting infinitely close to this red line, so I'm either going to go up and look something like a parabola, or I'm going to go down and look something like a cubic. I just don't know which. So let's start over here. Let's grab an x value. -4 is a good one. Don't go big. Stay close to the asymptotes. Make your life easy. So we're going to test x equals 4. -4, excuse me, because it is to the left of that red line. I think it's easier to plug in here than it is here. But it really doesn't matter. You'll use a scientific calculator. It's completely up to you. So we're testing y, x equals -4. Let's see what we get. Y equals, I'm going to plug it into the factored form. I get -4 plus 1 over -4 plus 3 times -4 minus 2. That gets me -3 on the top. And on the bottom, this is -1 times -6. Oh, my graph goes through the point -4, -1/2. You see, this is why we started this lesson yesterday by plugging numbers in and seeing where we were going to land. Because even when things get more challenging, you are still going to have to revert to plugging in numbers. So -4, -1/2 puts me right here. That tells me my graph exists below that green dotted line. I have to get infinitely close to the green dotted line. I have to get infinitely close to the red dotted line. The graph looks like this. Good enough. That is good enough. Earlier in period 1, somebody asked me, so doesn't that guarantee that its counterpart will be in the top? And I said, no, it does not guarantee that. You have to always check. Okay? There is no guarantees here. But next, I'm going to check a number between 0 and that red dotted line. I think x = 1 is a prime candidate for that. Let's see what y is. It's going to give me 1 + 1 on top. It's going to give me 1 + 4 times 1 - 2. That is 2 over 5 times -1. You look like you have a question. Oh, I just wrote the wrong number. Is that what you're saying? Yeah. Got you. So it won't be -4, it'll be -5. Excuse me, it won't be -5, it'll be -4. There we go. I'll be okay. 1 + 3 is 4, and 1 - 2 is -1. So you get -4. So what we have here is, oh, -1/2 again. That's a coincidence. I 100% promise you it's coincidental that we got the -1/2 again, okay? I don't want anybody to think that something crazy is going on that I'm keeping from you. But that coordinate was at 1, -1/2. That was right here. So that shows me as I got closer to this red line, I'm going down because it was below -1/6. So we got to go do this. Whee! So it's somewhat like a cubic in there, isn't it? It's not a cubic, but it behaves like one. And then lastly, we got this zone over here we need to check. I'm going to use x = 3 because I like my numbers to stay small. So I'm testing x = 3 to see what y value I get, and I'm plugging in right here. And hopefully I can do the basic math and not screw it up this time. 3 + 1, 3 + 3, 3 - 2. Well, all those are positive numbers. That already tells me I'm going to be above the green dotted line. But just in case, I have 4 over 6, which is 2/3. So 3, 2/3. I don't care, whatever. It's like here somewhere. The point is, it's above that green dotted line. So we're going to do this. Ta-da! And I forgot that I was going to show you this on Desmos, and I'm recording with the wrong program. So the video just won't get to see it on Desmos. This is correct, but I do want to show you guys in room. Boop, there it is. See? That's the graph we just did. Pretty cool, huh? Nobody's impressed. I mean, I am. I thought it was pretty cool. Okay. Yes, ma'am.
So the middle graph goes over the horizontal asymptote?
So the thing in the middle is because it's talking, in the middle, you're close to x = 0, right? An end behavior asymptote only describes what you're behaving like at the end of the graph. That means that way and that way. It doesn't tell you anything about the middle of the graph. So I don't want you to think that an asymptote is something you can't cross, because rational functions cross their end behavior asymptotes all the time. You know where they do it? Around x = 0. They do it at small values of x, because the end behavior asymptote only describes what they're doing at the large values of x. So it says, hey, if x is really, really, really big, I'm going to get close to the value y = 0. Doesn't tell us anything about when x is small. Okay? Now, a vertical asymptote is still a structure we get infinitely close to. It just so happens, though, that they're domain restrictions, and that's why we can never cross them. But it's not because they're quote-unquote an asymptote. Asymptote in mathematics just means I'm going to get really close to this thing. That's all it means. Are there more questions on what we did for this one? Are we sure there's no questions on it? Because I watched people's eyeballs melt and brains smoke in first period when I did this stuff. And they're my highest scoring class for Algebra 2.
Did you just like pick random numbers? Like you just like go with whatever you thought?
No, I didn't pick random numbers. I explained the ones I chose. I'll explain it again. I chose -4 because it's close to the asymptote, because I don't want my numbers to get too large. I chose 1 because it was between 0 and 2 to show me if I was going up or down. And I chose 3 because it was close to the asymptote, because the further you go, the larger your numbers are going to get. Or like this, like they're either going to get really, really, really close to 0, or they're going to get really, really, really big. So I stay close to the asymptotes. Okay? It wouldn't have mattered if I had picked -7. I still would have gotten a negative y value, which would have told me I was under here. And it wouldn't matter if I'd picked 9. I still would have gotten a positive y value, which would have told me I was above. But I didn't want to have to work with big numbers in my fractions. So I should stay close to the asymptotes. That way your numbers don't get big. Otherwise, it doesn't matter. More questions? So let's do something that's not linear. This one is quadratic over quadratic. And just like last time, I'm going to write it as a stacked fraction and write y equals. Yeah, I turned the page. Yeah. Okay. First, let's talk about behavior. End behavior. Allow x to get really, really, really big. X is so large that -2 and -9 stop mattering. When you reduce this fraction that you could still see, what do you get? 2. That's why this thing's end behavior asymptote is y equals 2, which happens to be a horizontal line. Or you could try to memorize the rule that the degree of the top being equal to the, that's a B, being equal to the degree of the bottom makes you do leading coefficient 2 over leading coefficient 1. So your end behavior asymptote is horizontal. That y equals 2. Now that we know what the endings of our graph are going to behave like, we need to figure out where this graph is even allowed to exist. So factor everything that you can factor. This, did I keep going in black? I did. This has a GCF. And I hope what you see is a special case on top and bottom. Difference of 2 squares on the top and the bottom. Like that. And once again, nothing simplifies away. Nothing crosses out. So since I'm not crossing any x's off the bottom, I don't have any holes or deleted points in my graph, also known as removable discontinuities. I don't have any holes / deleted points / removable discontinuities. But I do still have 2 x values I'm not allowed to use because they're going to make me divide by 0, which means I have 2 vertical asymptotes. At what x values can I find my vertical asymptotes? -3 and +3. I have 6 zones then. My graph is going to take up at least 3, but at most 4 of them. Oh, by the way, I said that for the last question, and you see, we occupied 4 of those spaces. Same thing's going to happen here. We're going to occupy at least 3, but at most 4. I'm not going to show you more than 6 zones. And I'm going to be real with you, I don't think I've ever done anything with more than 6. You could. I've just never bothered. And I'm such a nerd that I might even make myself one later just for funsies. It's not something you have to know. It's going to happen on its own because we're going to put that values in and we'll see it occur, you know. So it's not like I need you to memorize it. All right. At this point, for the last question, we started figuring out where our graph was crossing axes, right? The y-intercept is always the easiest to find in my mind because all you have to do to get the y-intercept is realize that if you're on the y-axis, x is 0. So if all of a sudden x was 0, what would the top and bottom of your fraction give you? What would you have on top? -2. What would you have on bottom? Is it that none of you know, or is that none of you care? I'm asking a question to my class. If x is 0, what is on top? -2. If x is 0, what is on bottom? -9. -2 over -9 gets you positive 2 over 9. I could record videos at home and have nobody talk to me. Like, why would I do that here? I'm trying to teach you guys. I'm not going to be recording these videos if you're going to keep ignoring me. Gives me 2 over 9. That is a positive number. It's 0.2 repeating. You make that dot large enough and nobody can argue with you about where you put it. This graph has 2 different places where it crosses the x-axis. I know that because when you're on the x-axis, y is 0. And if y is 0, that means the fraction equals 0, which means the top had to equal 0, because that's the only way a fraction can equal 0. So the 2 places where the top of this fraction equals 0 are the zeros of this polynomial up here. They are. For everybody, where is this one 0? -1, and this one? Positive 1. Good. So we have x equals plus or minus 1. We cross the x-axis twice. So we already know what the middle of this graph looks like. We knew it couldn't come back up because if it came back up, it would have had another x-intercept. So that forces this thing to have what looks like a quadratic in between. Now all we need to do is test values. I need to know what's going on back here, and I need to know what's going on out here. That's it. I already know what's going on in the middle. So I'm going to grab -4 and +4 because I'm trying to stay close to my asymptotes. We're going to test those 2 numbers out. And I'm actually going to substitute here because I only have to plug in one place in the top and one place in the bottom. Let's test -4 first. Y equals 2 times -4 squared minus 2 over -4 squared minus 9. That's 2 times 16, it's 32. Minus 2 is 30. And on the bottom, 16 minus 9 is 7, right? 7 goes into 30 a little bit more than 4 times. Because 7 times 4 is 28, right? So that gives us the coordinate -4, 4-ish. So that's up here. And we know that my graph does this then. Now all we need to do is get a value out here. Test x equals 4. plug it in. Y equals 2 times 4 squared minus 2 over 4 squared minus 9. Guess what that's going to get me? Exact same thing. Did you notice that all of the exponents on your x's were even powers? You know what that tells us? It tells us that our function is an even function. That means it's symmetric over the y-axis, if you can remember back towards the beginning of the year. So I am not surprised that it's exactly the same on the left and right of the y-axis. Not surprised one bit. Symmetric over the y-axis. Not bad, right? I have 8 more minutes. Do you have questions on this one? Is everybody cool with it? Everything makes sense? And when I say everything's made sense, I mean like you understand why I'm doing what I'm doing? Because if you're just trying to memorize processes, this is going to go very badly. We don't want to do that. You know what? I'm concerned that I'll have to rush through this question. Nobody cares what you agree to. I am concerned that I'll have to rush through this question. So I think I'm going to call it there because I need... you hush up. Everybody shut up. I don't want to hear anybody's voices. Yeah, this is the one time I don't want you to speak.